Okay, I think we'll get going. People are still joining, but we're getting up to a reasonable number now, so we're approaching some kind of critical mass to begin. So welcome to the Transforming Foundation Industries Network Plus event, which is in collaboration with the KTN today. It's a workshop which is going to be on sensors, controls, and digitalization. This is a critical part of the activities that we have at the Transforming the Foundation Industries Network Plus. And one of the pivotal things that we need to do in order to increase the sustainability of the foundation industries in the future as we move towards net zero. Could you advance, Debbie? Sorry, I tried to advance myself, but you're in control of my slides today. I think I should introduce the Transforming Foundation Industries Network Plus team before we go any further. We've been around for about 9 months now. We started, perhaps coming up to 10 months with October. And we started on January 1st. We're part of the Industrial Strategy Challenge Fund. And I'm the principal investigator, Professor Ian Reaney from the University of Sheffield. The Deputy Director is Susan Bernal-Lopez from the University of Leeds. William Sampson, Cameron Pladle-Pierce are my co-investigators, as well as Susan, of course, is a co-investigator. And we have Chris MacDonald of the Materials Processing Institute as the Independent Advisory Panel Chair. Our industrial chair is Chris, who's been very helpful and very useful with discussions as we've progressed through to this date. You've been dealing with Deborah Froggatt, who's the marketing officer for the TFI Plus grant, and Neil Lowry is the network manager, the program manager, who looks after the day-to-day running of this particular network. So what's our remit as the Transforming Foundation Industries Network Plus? Thank you, Debbie, for progressing the slides. Our core aim is to identify and co-create with the foundation industries new science that enables transformation towards a more sustainable, cost-efficient products and practices. There's multiple ways we're going to do that. You're attending one of those ways, which is create interest and activity around key areas such as digitalisation. But we also have a focused series of mini project calls, which we issue each 4 or 5 months in the cycle of the TFI Plus. And we've had 2 to date. I'll go through those in a second, what we've done. So it's a double-edged attack on this important problem of transforming the foundation industries. It's creating a network, creating and linking people together to try and address and understand the issues that surround the foundation industries and the essential transformation. And also we have £1.4 million of monies to be able to provide towards mini projects that enable that transformation in various different ways. So what are the key, no, can you go back, Debbie? I'm not quite finished. Thank you. What are the key areas? Well, we're focusing on multiple areas. Today it's going to be digitalisation, which is here represented as manufacturing informatics on this diagram. But equally, we look at resource efficiency, and we're just concluding a call in that. And we've recently had a workshop on that. Next generation processes, circular economy, and we also delve into issues surrounding equality, diversity, inclusion, and policy and advocacy for the transformation that is required for the foundation industries. We have about 400 members to date, and we hope that once you have listened to the talks today, that you feel inspired to join the TFI Plus and become a member and help us to make this transformation across the United Kingdom. As I've said, we have already had 1 full call completed, and we have issued about £270,000 of projects, and we are now just completing our second call, and we will be issuing approximately the same amount of money in projects. Last time it was 6 projects. We anticipate 6 projects at least will be funded this time, of course, subject to quality of review. Next slide, please. So where are we? I mentioned that we had an official start of the 1st of January. It was a hard start. We had to get going very quickly and get up and running within a couple of months, which we were able to achieve. Our launch event was on February 2021. We had our first workshop on road mapping to discuss with the community where we were in terms of the direction of travel for transforming the foundation industries, and you can find the outcomes of that online, and you can link to that through our web pages. We had our first project call, which was on energy efficient manufacturing in May. Energy efficient workshop was just after that. Unfortunately, we can't always time these things correctly, but we had an energy efficient workshop just after that. We had a resource efficiency workshop, a circular economy workshop, immediately prior to our second call on resource efficiency and industrial symbiosis. So there was a better connection there between the workshop and the call coming out. And now we're at the point of discussing digitalization, sensors and control. And this precedes, as I've said, a call coming out in early New Year, early 22, which will contain a request for projects in this area. So keep an eye on that. That will be coming out in the new year. We'll be advertising it very soon. We hope that the participants and potentially the speakers today are interested in submitting some of the excellent research to that particular call. Next slide, please, Debbie. So if you want to contact the Network Plus, talk to us, or listen to what we're doing, there's multiple platforms. We have the email address, which will get you to Debbie and Neil, and it will be passed on to me if appropriate. We have our webpage, which is, as you can see here, is the TFI Network Plus.org site. And we have a Twitter handle, which is at TFI Network Plus, which is run by Debbie. Okay, so what's happening today? So this is the agenda for today. We have 5 speakers today. The plan is for me to introduce the Network Plus and to thank the Knowledge Transfer Network for helping us coordinate this, and that has clearly been done. But we then have 5 speakers, which are Professor Theodossiades, Dr. David Armstrong, Dr. Michelle Ramades, Dr. Yufang Lai, and Professor Jishang and Alison Norden. They'll be speaking in a linear fashion. These are not parallel sessions today. And each talk will be approximately 15 minutes, followed by a 5-minute discussion and question session. We'll have a 5-minute break, and then we'll have a round-up session at the end of Q&A, if that is appropriate. And we will take general questions about today's webinar and hopefully address them to the speakers, or perhaps you can ask questions about the forthcoming call to this area, which will be announced very soon. So I'm going to move ahead and quickly now introduce our first speaker, Professor Stephanos Theodossiades, and please forgive me, Stephanos, if I have not pronounced that as I should. I hope I've got close. He'll be speaking on self-powered sensing for digitalizing foundation industries. Are you going to use you're going to do the slides yourself, or are you going to get Debbie to forward them?
I was hoping to use my slides.
Okay, so Debbie can hand over the control to you, Stephanos. And whilst that is happening, I can introduce you. Stephanos is a professor of nonlinear dynamics since 2015 at the University of Loughborough. He achieved his PhD from the University of Thessaloniki, mechanical engineering. So if anybody knows anything about Thessaloniki, they'll know that the University of Sheffield actually has a small international campus there as well. So I do travel to visit. His particular interests are powertrain engineering, powered sensing, virtual prototyping of medical devices. Stephanos is a member of IMECE and of ASME, and he's associate editor of multiple scientific journals. So please, when you're ready, Stephanos, if you can go ahead.
Ian, thank you very much for your kind introduction, and I would like to thank the TFI Network Plus, KTN, for giving me the opportunity to present the idea of self-power sensing for digitalizing foundation industries. Also, on behalf of my colleagues, Dr. Amal Hajai, Dr. Herling Fu, and Dr. James Flint, who were all from the Wolfson School of Mechanical, Electrical, and Manufacturing Engineering at Loughborough University. May I check before I get into the core of the presentation that the slides change and that you can see my sensor and you can hear me well, please?
Yes,
Ian,
we can see and hear you.
Thank you very much. Thank you. Now, this is the outline of my presentation, a brief introduction to describe the topic. Then I will establish the connection between self-power sensing and vibration energy harvesting. Vibration is the form of energy harvesting that I would focus in this presentation. And finally, we'll conclude with some bespoke concepts of microelectromechanical systems sensing for measuring, for detecting different gases and air pressure. So first, what do we mean and how can self-powered sensing support the digitalization of the foundation industry? So as the keyword says, these are systems, sensing systems that are able to generate the energy that they need to function by themselves by absorbing energy from their environment. For example, solar energy, thermal energy where there are significant thermal gradients, wind energy, or vibration energy or motion energy from the source, which is usually the host system where we want to monitor. So they don't need any external source, such as batteries. They don't need wiring to be connected to an external source. And these systems that we call, these systems generally comprise an energy harvester, which is a little device that is able to communicate with the host and extract small but useful amounts of energy from the host system. Now, for energy harvesting, we talk about milliwatts in the best case scenario, but with the progress on sensing, microcontrolling, and so on, then this is more than sufficient. Then this energy is used to charge a capacitor or to be stored in a battery locally and to activate, to trigger a sensor like temperature, humidity, to measure a property that we wish. The information is processed. It can undergo signal conditioning in the case of motion detection, for example. Data can get stored and can get communicated wirelessly to a user. So imagine that this is just a node, and imagine the deployment of hundreds of nodes like this in a network, forming a network in an environment like a factory here that can extract information from storage of goods, from the supply chain, from packaging, from cobots, and so on to inform the users. Now, what are the advantages of this type of self-power sensing? First of all, these networks enable the industry of things. Information can be collected from inaccessible locations. We don't need to access those self-power sensing systems frequently and change batteries. So all sorts of useful data can be collected from many locations in a factory, for example. That also means that we monitor properties, processes and machinery and so on, and we're able to intervene and do maintenance in a predictive manner, not every scheduled intervals, for example. That eliminates maintenance costs and manual inspection. As a result, the efficiency of the system operation is improved, the process gets digitalized, and we have better control, productivity, and optimization in the production line. Now, I mentioned the energy harvesting device here, which is a key part of this node, because it communicates with the environment to extract the useful amounts of energy that we want. and I will concentrate, as I said, on vibration energy harvesting, where there are two main transduction concepts. One, the electromagnetic, where we have the motion of a magnet in the vicinity of a coil with hundreds of turns, and that changes the magnetic field of the coil, and that produces voltage at the end of the coil, which is the energy that we use to power sensors. Where is the motion coming from? Is coming from the host system, the machinery, for example, that it vibrates, and that sets the whole device into motion, and we can retrieve tens of milliwatts of power. The piezoelectric concept, on the other hand, is less bulky, but it can retrieve smaller amounts of energy, hundreds of microwatts of power, and includes a beam that again can set a beam with a tip at its end, which can set into motion again by the vibration of the host. The beam is dressed with some piezoelectric material, which when it gets deformed, then it produces voltage that again gives us the useful power. So both concepts depend on the external excitation, and the aim here is to make the magnetic mass here, or this tip mass, to operate at conditions of significant vibrations, at resonance conditions. Because the higher the velocity, the higher the velocity of those two masses, the higher the amount of energy that we can obtain. That can be seen here. This is the velocity against frequency. This is the classic resonance, linear resonance curve. And this is a useful region. Above certain amplitude of motion, we can retrieve significant amount of power. But in machineries or in processes, the properties of the external excitation, the features of the external excitation are not fixed. So that frequency can drift significantly. And then we get away from the region we can retrieve significant amounts of power, and we don't get much, really. How can we deal with the problem? If we design the energy harvester in a non-linear manner, so that instead of having this linear resonance curve, we follow this skewed resonance curve, then the frequency region when we can retrieve significant amounts of energy increases. And there are many ways to do that. One way, for example, for a translational vibration energy harvester is this, where a levitating magnet between two fixed magnets receives motion from the base, and there are, again, hundreds of coil turns around the levitating magnet. This bulky and ugly prototype is fixed on a vibration shaker. So when there is motion on the host, on the base, then that motion is understood by the harvester, and the energy is sufficient to power this little light. The same prototype, if it is installed near an internal combustion engine, is able, because there's more energy present here, is able to power two engine coolant temperature sensors and two air intake temperature sensors. This is a translational vibration energy harvester, which takes its motion by lateral vibrations of the magnet. This is the same concept that is mounted on a shaft, on a rotating shaft, and because of the change in the position of the harvester as the shaft rotates and the change of the effect of gravity, then we're able to harvest energy from three different resonance conditions along the speed range of the shaft. This harvester has been mounted on a greasy gear per rig here, and again the actual vibration energy harvester is much smaller than this casing that has been used just for proof of concept purposes. This is the result of the experiment. That's the first resonance zone. The second and third resonance zones are merged, and we can see that for a speed region up to about 800, 700 RPM, we can harvest significant amounts of energy. A third concept is this one that includes a housing mounted on a shaft. Again, it's a rotational vibration energy harvester, and that the housing contains a pendulum that is driven on these paths with the help of some rollers. So when the housing rotates with the shaft, the pendulum follows horizontal vibrations. There are two magnets on top, and there is coil at a gap at a certain distance. The magnets are moving, the coil is fixed, and again, we have the same method of voltage being produced at the ends of the coil. Now, this is the vibration energy harvester. You can see it here at the end of the experimental rig, connected to a power management board, the microcontroller, and the temperature sensor, up to about 4.5 milliwatts RMS energy that we could retrieve at 2000 RPM. This is a demo of measurements taken from the real system. So you see different curves here. The green curve is the AC voltage from the harvester. The purple curve is the capacitor being charged. So when the capacitor gets a peak here, then it's fully charged, then it triggers the microcontroller. The microcontroller triggers the temperature sensor, then measurement is obtained and is being sent to the computer via Bluetooth connection. So when it reaches the peak, then this value of temperature is going to be updated. Then the capacitor gets discharged, and so on and so forth. And how quickly the whole thing, the whole loop repeats itself depends on the amount of energy that comes into the system. Here, it takes just a few seconds for the shaft rotating at 1650 RPM. This is a piezoelectric vibration energy harvesting concept, and is based on the rotation of the host system that includes a magnet. Let's call it the driving magnet. This is the host system, the white disc on the experimental apparatus on the top right. And then that magnet plugs a magnet that is on the tip of this beam here. And there's another fixed magnet on top that is there to introduce conditions of nonlinear resonance. So piezoelectric material all along the beam that creates the energy that we want. The idea is to make the piezoelectric harvester, again, oscillating like crazy from one end to the other end constantly, with the force of the magnet, of the driving magnet being sent to the tip magnet every time that it passes this position. And this is a velocity displacement graph, which shows that the tip magnet is moving from one position to the other. Particularly good harvester for low frequency random vibration motions. Another way of harvesting energy is by using radio frequency power. And usually factories are noisy environments, and industrial processes create considerable radio frequency power that can be harvested using some rectenna. Rectenna is an antenna with a built-in rectifier. In this case, the harvested energy that you can see here reaching a peak at 5-point-something milliampere, with the help of a microcontroller, is fed into an e-ink display. So that's a different concept of harvesting energy. That's another concept that can be used for obtaining measurements from sensing, particularly sensors that are embedded in metallic structures like nuclear waste containers. It's not self-powered, but I thought of mentioning that here. So, say we have the sensor here in the container, so a transmitter that can reach the top of the container with the help of this drone, and it can send ultrasonic waves that can penetrate the metallic structure to realize power and data transfer here. The experiment that was set, including this transmitter and receiver in the bottom right corner, led to a maximum output power of 1.73 milliwatts. But we have to note that the capability of power transfer changes with the thickness of this plate. The lower the plate, the higher the capability, as we can see here. For blue means 6 millimeters of thickness, while 10 millimeters of thickness means the orange curve. Finally, I would like to conclude my talk with this microelectromechanical systems sensing concept. So this is a concept of a MEMS sensor to detect air pressure and concentration of surrounding gases, which is suitable for environmental monitoring, air quality, control of chemical process, personal safety. And in contrast to conventional sensors, which require special coating, MEMS have significantly lower size. Look at the dimensions in the bottom right in micrometers, while conventional sensors cannot really go that low in terms of size. The idea is to hit a micro bridge, that MEMS bridge, by establishing voltage between those two anchors in order to bring this micro beam into buckling conditions so that its lateral stiffness is almost zero. And you can see that here in the frequency graph, that the frequency decreases, reaches almost zero at the buckling point. While when the air pressure increases, then we have a frequency increase, and with appropriate tuning, this is how to determine the size of the pressure. And finally, the same concept can be used for detecting the gas concentration and the particular type of gas with respect to the thermal conductivity of the gas. So the resonator is exposed to gases with higher or lower thermal conductivity compared to nitrogen, and that, as a result, reduces or increases the axial stress here in the microbridge. And that alters the resonance frequency. So we see examples of how the first natural frequency changes and the second natural frequency changes. Here, a shift in the first mode, this is the buckling point for both beams. A shift in the first mode quantifies the concentration of the gas, while a shift in the second mode is telling us if it has higher or lower conductivity compared to nitrogen. So these are experimental results for detecting helium and the concentration of helium compared to conventional sensing. So the concept can follow pretty well the concentration, and with the shift in the second frequency, second mode frequency, it identifies that this gas is a gas of higher thermal conductivity. In the case of argon, which is a gas of smaller thermal conductivity, there's no significant shift. Now, I hope that I described broadly the idea of how self-power sensing systems can be designed for a variety of applications and for foundation industry where particularly input energy, motion, vibration is available. Of course, these are bespoke systems and their design depends on the requirements, the location, the machinery, information, where industry to retrieve information from. We will be very pleased to discuss any requirements. Thank you very much for your attention.
Thank you very much, Stephanos. I would now like to open the presentation for some questions. If you could put them in the chat. We have a few too many people to raise hands, so if you could just drop them into the chat. We have one from Bhaskar. Do we end up spending more energy input in both examples? So could you comment on that, Stephanos?
Yes, generally, the amount of energy that these systems need is very small. So we talk about milliwatts, and this is excess of energy that otherwise goes wasted. So in the case, for example, of the rotating shafts, the shaft motion was not affected at all, really, by the system that we placed there. So if I understood the question correctly. So we don't interfere. We actually don't interfere on the operation of the system. We don't consume energy that is good for the operation of the system. We just work with the residuals.
Thank you. I think yes, that's my understanding also of these systems. So yeah, that's absolutely right. So this is another question from Chris Oswin. Have you looked at any systems powered by waste heat? I guess that's referring to thermoelectrics, I suppose.
The applications that I was dealing with didn't include significant gradients, thermal gradients. If those are not in place, then you cannot get significant power harvested from the application. You need really strong thermal gradients there. But I'm sure that there are systems with thermal gradient and where this can be applied.
I think most thermoelectrics need 800 or 900 degrees C, dropping down to significantly lower temperatures to get something out of them. There is another Q&A at the end, but I'm going to sneak in one question. What is the kind of PZT you're using, Stephanos? Have you had a look at the grade of PZT, the kind of outputs you get, kind of temperature, upper limit of operation?
I don't remember from the top of my head. I will ask my colleague, Hailing Fu, and I will get back to you at the end of the Q&A.
What we find that sometimes if you buy standard cantilevers, then they're not necessarily optimized for the temperature range you want, or the and some systems, you know, if you're operating at low temperature, you can get significantly higher outputs based on the type of PZT that you have. And PZT is a bit like steel, you know, there's multiple formulations of different properties.
It's definitely hard material, harder than people may think that it is. But what I want to make the distinction here between the electromagnetic and piezoelectric. If someone wants significant amounts of energy for all sorts of reasons, the type of data that you want to obtain, for example, if you want to obtain motion and continuously, instead of obtaining a single value of humidity or temperature, is a very different story. Because you need to get significant amount of data, you need to post-process those data with some signal conditioning and so on. So it's a very hungry application. And if the requirements are a very low amount of energy and very low size, then of course PZT is a way forward.
Okay. I have multiple questions for you, Stephanos, but for the sake of the time, I'm going to move on. So thank you very much for that. That was really interesting, and it comes across something that I've dealt with, of course, with the piezoelectrics as well. So for me, that was very interesting as well.
Thank you.
So thank you very much. Okay, so we're going to have our next speaker now, who's going to be David Armstrong, who's going to give a talk on photonics for sensors, controls, and digitalization. Digitization, forgive me, I say this wrong all the time. Dr. Armstrong is a business development manager at Fraunhofer Centre for Applied Photonics in Glasgow. He specializes in optics and laser physics. He graduated from Strathclyde with a PhD in laser physics. He's had multiple different roles in technical and business management in the and semiconductor, telecommunications, laser optical sensing companies. These are all within his purview over the years. And clearly he is very experienced in this areas of photonics for sensors, controls, and digitization. I'm going to hand over to you, David, to begin your presentation. Are you going to do your slides yourself?
I am, Ian. Yeah, I'm just checking. You can see slide number 1, and you can hear me okay.
If you can just, as long as you've got control from Debbie, that's okay. Thank you.
Okay, thanks, folks. Thanks for the introduction, and thank you very much for the organisation of the event and the opportunity to present. So, I'm David Armstrong from the Fraunhofer Centre for Applied Photonics, located here on the University of Strathclyde campus. So I'll explain, if you don't mind, briefly what on earth we are, because we're slightly unusual. We're in the jargon, a research and technology organisation, an RTO. And we're also a UK not-for-profit company, so you can find us in Companies House, for example. But given the name, the Fraunhofer name, we're also a legally independent affiliate of the Fraunhofer Society, which is arguably, Europe's leading independent research organisation with a very broad range of interests across many different themes. But what we do really is we provide professional R&D services, and I would emphasise the D for development rather than are for research. We don't really do research, we do development in the field of photonics. So that could mean development of lasers and sources, which is a background many of us have in the centre, but increasingly systems and instrumentation, which are used to measure things. So some of the photographs here maybe give you an idea. Top left is hydrogen sensing developed for solar fields and actually deployed in solar fields. Top right, oil quality monitoring, lubricant oil quality monitoring with an industrial partner. Bottom right is actually a miniature credit card size laser for quantum technology applications. And on the bottom left, wind LiDAR deployed in a wind turbine in the North Sea. So we design and build systems which can be deployed in reasonably demanding circumstances. So we work with and for industry. We have a mandate to help industry and help UK PLC move on with their technology. If you're familiar with TRL levels, well, we can take things hopefully from some laboratory benchtop setups. This is a classic optical table type thing. We can engineer that up to a proof of concept, something that might be portable, manhandleable, and indeed all the way up to product technology with suitable partners. So we span classic valley of death is the phrase that's used very often in terms of technology. So our capabilities, as mentioned earlier, yes, we design lasers, but more importantly, both systems and instrumentation for industry. So as just a brief intro, very brief, why photonics? Why might photonics be of use and benefit in some of these circumstances? Well, it's the ability to sense something without touching it, without taking a sample, without taking it to laboratory, without doing wet chemistry. So if that sounds a little bit esoteric, well, if you have an iPhone or many other devices, then you will have a LiDAR scanner. And their LiDAR is the optical equivalent, if you like, of radar. So this technology is out there and fairly ubiquitous, and it's in your pockets, and it's out there. So if I can just rattle through a few examples, most of our work, but some of our other people's work, is we have quite a bit of background in substance detection and things like situational awareness in homeland security, but also seeing the invisible, be it in the nuclear sector or industry, and a number of partners that we've built up over the years that we've worked with. So very briefly, the interaction of light with matter, a very simplistic diagram, but you've little blobs here, different colors. The different colors represent the different wavelengths of the individual photons here. And if these photons interact with, in this example, a cloud, but it could be a substance, it could be a granular material, it could be a residue, it could be a liquid, what have you. Some of these photons, blobs, will be absorbed preferentially rather than others, and you can detect and sense what's left, and that gives you, for example, an absorption spectra. That's very simplistic, but bear in mind there are other techniques we can use, fluorescence, Raman spectroscopy, and so on, but I don't have time to, if you like, give a broad overview of all the different techniques, but it's basically applying light to a substance and using the information to gain some insight there. So, for example, automated pharmaceutical validation is a project we carried out with one of our sister Fraunhofers in Germany. And the idea here is to look at, if you like, capsules or tablets and verify what they are. The motivation really comes from sort of personalized medicine, where you have your own range of tablets for morning, noon, or night. And there's a demand to make sure you have the right tablets in the right packaging as they've been processed. So in a sort of brief overview, the concept, you maybe have a production line moving tablets. You have a camera system. Obviously, you're going to need electronics to control this overall setup. Use the camera to detect the presence and location of the tablets, for example. Use that information to direct a laser at the individual tablets, and then detect the light that comes back. And from that, you can ascertain the absorption spectrum and perhaps the actual type of tablet that you've looked at. So in practice, we put together, our own miniature conveyor belt system, shown here with some benchtop systems. And if I can get this video to play. So what we have is the blister packs with the lid off, sliding past. And if you can actually look, you might be able to see a laser beam. There's actually a tracer beam in here because this is mid-infrared wavelength range. You can see a tracer beam that's been directed at each individual tablet. And you will notice that the pack is coming in different orientations. We're actually able with the camera system to find where the tablets are. And then we can ask ourselves, what is this tablet? Is it ibuprofen, aspirin, paracetamol, or what have you? And we can carry out that analysis and verify which tablet is which. So that gives you an idea. So of if you like, perhaps process monitoring type applications. We're using similar technology in applications on granular material, actually in the nuclear industry for remediation of sites. So what is present in this material that's presented to the system, perhaps in a conveyor belt. So that's the kind of work we have ongoing at the moment. I'll move on to another example of standoff sensing and detection using photonics, which is a project, in fact, a European Union project, Horizon 2020, on the detection of explosives. So imagine you're if you like, a first responder to a suspected bomb factory, and you're presented with lots of different white powder, and you want to know what is what, and you don't have time to take it to a laboratory. So again, I'm drawing, if you like, the analogy between this kind of work and perhaps standoff detection in process environments. And what we built was a handheld device, which was, you point it at the substances, and it actually gives you a readout of what the substance is from a known library. So if I can show this video, for example, this is one of our colleagues. So you can see a tracer beam, the red beam, if you look very carefully, pointing at various substances, and in the panel that's mounted on top of the ray gun, let's call it, every time it goes pink, it's a recording, if you like, a match with a spectrum from its library, and it can detect things like residues on the little buttons on the bag there. Another example would be in the nuclear industry, detection of gases for condition monitoring. So in this, we have a challenge, which is, it turns out the stored nuclear waste gives off hydrogen. And we want to monitor that hydrogen in a storage environment where you're stacking these cubes several high in a warehouse type environment. And you want to produce some kind of map of the hydrogen concentration across the storage area. We worked with Sellafield on both developing and deploying this system. Basically, it uses time-correlated Raman detection. So Raman is a technique where if you shine light at a given wavelength on a substance, it may give out scatter light at different wavelengths, different colors, and the shift in wavelength is indicative of the species of interest. So if you can examine the light you get back, you can gain some insight into the type of material you're looking at, in this case, a gas. So we have an instrument, we send photons out, we get photons back, and from the photon arrival time, we can ascertain the position. From the photon color or wavelength, the composition, is this hydrogen, nitrogen, water, benzene, for example. And from the number of photons, we can ascertain the concentration that we're seeing. So it's a LiDAR type system. There's timing involved here. And there's also very low photon counting going on here, because if you send out very large quantities of photons per pulse of light, you may only detect a single photon, a few photons coming back. And in the quantum technology sphere, single photon avalanche detectors, SPADs, are coming to the fore and are available. And these allow you to detect low numbers of photons, but also importantly, they give you timing capability as well, so you can carry out the timing and the ranging technique as well. We've developed these systems and in fact deployed them in Sellafield in order to carry out hydrogen measurements. So a slight change of tack, but following on in the theme of this single photon detection and ranging, and this is work actually carried out by Gerard Buller's group at Heriot-Watt University, although we have experience of working closely with SPAD detector companies. And I won't go into details, but essentially what they were doing was using pulses of light and SPAD detectors to image, in this case, a clock tower at sort of 10-kilometer range. And the important thing here to bear in mind is the power levels, the optical power levels that we're using. This wasn't, if you like, it's a very unscientific term, this wasn't a death ray, this wasn't a really high power laser, this was a very modest optical powers enabling you to image at a distance. So how this might be of interest in industry, I think, would be situations where you're trying to image through turbid media, scattering, dirty environments with lots of scattering, where you're not going to get, if you like, a pristine picture of a process. So this is another example, again, Gerard Buller's group at Heriot-Watt, of detecting and imaging underwater. So this is a simple, plastic flange device, and without going into a great deal of detail, they were able to image this through what I could only describe, again, unscientifically, as a pea super, the kind of water where you would not be able to see the hands in front of your face. But nevertheless, with modest optical powers and using these single photon detectors, you can image surfaces, image items in circumstances where really you would not be able to see through this sort of cloudy, horrible environment. And that's another thing perhaps to bear in mind in industrial processes. The environment does not need to be pristine in order to use photonics. And finally, lubricants. We've done some work on detection of particles in lubricant oil, obviously important in so many applications, wind turbines as an example. So what you want to do here is detect the presence of, if you like, the little shards of gearbox material that are going into the oil. And without getting into details, this might be a technique where in the past you might have to take a sample, take it to a laboratory and do the analysis, look at, if you like, the particle counts, and gain some insight into the condition of the oil. What we did was we developed a system where we have a fairly simple LED source, a CCD camera, and we flowed the oil through a flow cell, and we're able to sort of histogram, if you like, the aspect ratio of the particles we're detecting, the length, and for example, shown here in this plot, and we developed a sort of standalone, fairly portable device for doing the oil analysis. I think this is actually a picture of my hands in that photograph. So hopefully I've sort of answered the question, why photonics? As I said at the beginning, it's the ability to sense without touching. That could be material composition, granular material, solids, liquids, gases, the ability to see through clouds, see through media that would otherwise be difficult to see through, and the ability to analyze fluids. Things that I've not mentioned in any detail would be things like hyperspectral or multispectral in a more simple system imaging. Structured light would be another thing that might be of interest in some of these industries. Wi-Fi, the optical equivalent of Wi-Fi, offering quite high bandwidth. And indeed, we're heavily involved in the quantum program in the UK, so quantum sensing, magnetic fields, for example, as part of this, if you like, seeing the invisible. So I'll draw it to a close there. Happy to answer questions if there's time, but also happy to engage offline by email. So thank you very much, Ian.
Thank you very much, David. That was really, really interesting. A couple of questions have come in. I think we have a little bit of time just to answer them before we move on. This is from Mohammed. Can you give examples, problems of photonic detection working in dusty environments? I think to some extent you did that towards the end, where you were talking about P supers, but yep. Can you expand on that?
Yeah, there is. So, I mean, I'm partly presenting an overview here. So, for example, Gerard Buller's group do a lot of work in detecting through smoky clouds. Quite a lot of this work is not surprisingly funded through DSTL. You know, I'm not giving anything away that's not in public domain, but imaging through smoke. Another classic example that people have done work in is, believe it or not, it's sandstorms as well.
Nice.
So one application, believe it or not, is helicopters landing in deserts, which you can imagine was something that was of interest and continues to be of interest. So it turns out lots of helicopters just bang into the ground because they can't see the ground. So that there's work, for example, to see through that sandy, scattered sand. So there it's quite an extensive area of work. Academic, in the academic terms in the UK, we're involved in it from a more translational research and development point of view. We've got a project ongoing. For example, one application is underwater imaging, which is a classic example of a turbid environment, but it doesn't need to be water. It can be horrible, smoky, dusty environments.
I guess the question is prompted by perhaps the environment sometimes around a blast furnace or in a ceramic factory, a little bit dusty.
That's partly why I presented it, because it's just so that people don't come to the conclusion that you need a pristine laboratory environment to see some of these effects. Okay,
well, that's a really good answer. Thank you very much. And this is from Mark Taylor. Techniques like Raman and SPAD, are they expensive to implement in a process environment? Can you comment on how they might be taken up by the foundation industries? So I guess cost is one of the things. Excuse me, my calendar just pinged then.
So, you know, a bespoke system at the moment would not be $1 price. So we're not looking at that kind of price level. But these SPAD systems are SPAD devices. They're semiconductor devices, so they lend themselves to fairly inexpensive volume manufacturing if they're taken up. So you've got the opportunity to perhaps piggyback on other applications that have high volumes if the foundation industries themselves can't generate that kind of volume. So some examples would be LiDAR, automotive LiDAR technology, for example. That's going to have a extensive uptake and might drive prices down. So what I'd say there is right now, if you wanted a system, it would not be $1. It would be, you know, a few $1,000s or pounds, but you have the opportunity to piggyback on some work elsewhere and demand elsewhere that could drive those costs down.
Okay, so thank you very much. That's a pretty comprehensive answer. It costs, but it's probably worth it, is what I got out of that.
Yeah.
Yeah. So I'm going to thank David for the talk again. That was really excellent. Any more questions for David can be done by chat or by his personal email. So please contact him directly, or we can discuss again at the end a little bit more and direct some questions towards all the speakers when we have the Q&A at the end. That was really, really great, David. Thank you. We're going to move on now. So our next talk is going to be from Dr. Nishal Ramadas. Is going to be talking about ultrasonic flow meters. Nishal is an instrumentation engineer. He founded HiMet Limited, developing instrumentation software solutions to enable transition towards net zero targets in the UK. So very, very pertinent. He is an expert in non-destructive testing. He holds a PhD from Strathclyde University. That's the second person today who's come from Strathclyde. And has a visiting honorary academic position at the University of Warwick at the WMG and Birmingham City University. So a very broad person who has multiple contacts across the UK. Nishal, are you going to do your own slides, or is Debbie going to follow them for you?
I managed to share, Ian. So.
Thank you. Okay, so you go ahead in your own time, and we'll take the questions at the end as before.
Sure. Thank you so much. I guess everybody can see my slides and hear me okay?
I can.
Yeah, thank you. So thanks for the introduction and inviting me for this talk. A quick overview of what I'm going to say. Very high-level introduction to sort of fluid flow, property measurement, and really basic, broad brush overview of ultrasonic flow metering technology out there. And I'll do a slightly unconventional way of introducing us and what we do towards the tail end, and see what opportunities this could potentially bring in from the kind of foundation heavy industries. So I guess most industries have to go through some sort of significant transition, particularly when it comes to high degree of automation to optimize their existing processes, whether it's to reduce the energy they use, whether it's to optimize the processes in a way that the wastage is minimized, etc. And what is really prerequisite for this is understanding the process itself, and process control equipments and process measurement technologies become very, very critical. Today, we are going to talk about fluid property measurement as a topic. And there are wide varieties of metering technologies out there, from Coriolis meters to ultrasonic to mechanical meters to electromagnetic and whatnot. At the end, they all give either some sort of velocity at a single point, volume or mass, and some technologies like ultrasound can do much more than just give you volumetric flow velocity. Flow volumes. And today we will be talking mainly about ultrasonic. Even in ultrasonic, just to not dilute too much, I've taken gas as an area to concentrate. So if you look at the gas metering technology as a very crude overview, you have some really small meters like the domestic gas meters or industrial gas meters you have in your premises that measure natural gas. At some point they have to switch to blended hydrogen and others, etc. And then you have industrial meters. Industrial meters, again, when you look at industrial gas meters, it's fair to say that ultrasonic and Coriolis are probably the two most popular metering types out there. And any technology or any meter that needs to go on a larger pipe, let's say 2-inch or above, I would say ultrasonics is probably the leading technology out there. And anything that needs measuring in a very tiny pipe, maybe Coriolis is doing much better there. And today we'll be focusing mainly on ultrasonic flow meters, so we'll restrict to that. Just a very short basics on ultrasonic flow meters. They're not new. They're existing for many, many years. Dates back to some early patents and German patents in 1928. They've been in use for many, many years. Commercial use, started in 1950s. And today, they are used in so many different applications. From small medical instruments to large industrial processes, etc. Obviously, because of many advantages they bring, no moving parts, so many mechanical meters, etc., are getting replaced by ultrasonic meters because they are, essentially, very low maintenance, and they're also a metering type that works over a very broad range, from the lowest flow you can measure to the highest flow you can measure. It's known as or referred to as turn down ratio. It's a very wide turn down ratio compared to mechanical meters. So, for example, turbine meters, etc., you typically 10:1 is the kind of turn down ratio you talk about. Compared to that, an ultrasonic meter goes several hundred to 1. So instead of having a bank of many turbine meters, you could potentially have one meter doing the measurement. They're also fast, bidirectional. So if there are layouts you need to change to be able to replace 2 pipelines carrying stuff into maybe one that can switch directions to reduce capital or simplify some processes, ultrasonic again can be quite handy there. because you don't need 2 meters to measure on 2 directions. They are also very accurate. The current gas meters have uncertainty as less as 0.5% under very controlled conditions. In all practical applications, they're very low, a few percent, I would say. The biggest advantage for ultrasonic metering is they are kind of non-intrusive, non-invasive nature. So they don't really interfere or produce some problems with the actual process you're measuring. In my opinion, the biggest benefit from ultrasonics is ultrasonics also can give you a lot of additional parameters that can be useful. For example, speed of sound. Instead of just relying on the arrival of the speed of sound to calculate the flow, you could also have that infer or identify what's changing in your property. So if you have a mixture of gas going through a pipe or some pollutant added to your material that you're supplying to your processes, speed of sound is a very good parameter to identify that shift when the gas composition or the fluid property changes. So it's also lends itself, as a metering technology, lends itself really nicely for diagnostic purposes, not only to monitor the condition of the meter, but also to monitor any changes or drifts in the process itself. When you look into ultrasonic meters, there are again so many different types of ultrasonic meters. There's some very non-common ones like cross-correlation meters and stuff like that. We won't discuss that, but broadly, you classify them into Doppler or versus transit time or time of flight techniques. Everybody knows Doppler from high school physics. The frequency changes when a flow happens or when something moves past you. So essentially the same principle. You have an ultrasonic sensor sitting and listening to the fluid going in a pipe, and the flow, the frequency shift of the signals that's bouncing back from the fluid, that relates to the flow. Very common in medical and industrial liquid metering, purely because liquids by their nature have bubbles in them, which are very strong reflectors of ultrasonic beam. So because you're relying on a reflected beam here, that's essential. Not so popular in gas measurement. So gas measurement mostly relies on transit time measurement principle, where you're really looking at time of arrival of two signals, one going up the stream on another one going down the stream, and working out the differences between these two and deriving the volumetric flow. Of course, a very oversimplified example of how flow meter works. Large industrial meters are much more complex. They have temperature measurements, pressure measurements to compensate for variations. They have multiple transducer pairs that are kept in strategic locations so that the overall volumetric flow measured is representative of the larger cross section of the large pipe, etc. The other common type is also how the transducers are mounted, or common differentiation is how the transducers are mounted onto the process spool piece or measurement spool piece. It's either a clamp-on device where you have a device just literally with Jubilee clip type arrangement attached to the exterior of the pipe, and they are quite good for certain processes. Again, very common in liquid industries, not so much in gas, because it's totally non-invasive and non-intrusive. But very common is the other type, which is wetted. As the name suggests, the transducers are inserted in a hole, and they're touching the fluid. Again, they're very minimally intrusive in terms of they won't affect the flow or anything like that, because usually they are positioned as it's shown in this picture at a very close to the inner diameter of the pipe. Like any metering technology, there's not one metering technology that might be suitable for certain processes. Ultrasonics has a lot of merits, but also lots of challenges. Some of the challenges are captured in this slide. So if I play this video, I'm assuming you can see what's happening on the screen. So you could see there was some wave that's emitted here that's going into a pipe and gets bounced back, and it'll come back to this receiver here. But what you also see is a lot of energy gets coupled to the actual steel spool piece. So the challenge here is the receiver sensing the signal among all this crosstalk, both the mechanical crosstalk from the energy just pinging around in the spool piece, and also any electrical crosstalk that might exist in your pulse receiver electronics. Again, this noise in your in a process affects a lot. So where you install your ultrasonic meters, etc., will become critical. So if you have a valve, for example, installing a ultrasonic meter downstream from a valve is a bad idea, because valves are becoming more and more quiet because of safety concerns. But while they become low in audible range, what has happened in the development of valves is the frequency of the noise gets shifted to higher frequency, and they do interfere very well with ultrasonic flow meters. So even simple things like positioning your meters upstream a valve or away from some crazy double bends and things like that would help a lot. Another thing is gas. If you're measuring gas, property, fluid property, flow, etc. Gas is generally a tougher medium for ultrasound, particularly if you're switching fuel from, let's say, natural gas to hydrogen or some lighter gas. The acoustic impedance mismatch between the generator, the piezoceramic transducer, and the gas is very low, and often you need a really good transducer design to generate signal that can go through. I talked about flow profile variations, etc. So again, in a pipeline, where you install, everything matters, and of course, the effect of harsh environment, temperature, pressure, etc. And the other challenges, currently most industrial meters that serve ultrasonic industrial meters that serve areas such as oil and gas, etc., are a proven technology, but often is size and cost, etc., restricted from wider adoption for multi-point measurements and in other areas where maybe the cost of the equipment has to be very low. So again, things like low cost, efficient device with applications in a lot of different areas could be the way that ultrasonic flow meters need to move. With that very rapid introduction to the ultrasonic technology for flow measurement or fluid property measurement, I'll introduce HIMET. As it was mentioned earlier, HIMET's a very new startup. We're based within the Warwick Manufacturing Group, University of Warwick Incubator, and we are basically an instrumentation company. It's founded by 4 partners. Along with me, we have James looking after business development, Andy leading technology development, and Chelsea is our chief financial officer. We are essentially building this company to start making, design, and fabricating new instruments that help many industries move towards sustainable energy into the future. We picked hydrogen as a topic that we want to concentrate because we firmly believe that there's no silver bullet, and the future energy system and future process within industries are going to be quite complex and hybrid. And there'll be a lot of challenges, both technical and economic. And we feel that hydrogen has a role to play, a pivotal role to play in this for all the good reasons. The foundry industries and heavy industries already use hydrogen in quite a lot. So the technology and means to handle them, produce them already exist, even though the hydrogen produced nowadays are not from a green source. That is something, with sufficient investment and support, can be moved towards a more greener alternative. But most importantly, hydrogen can play a really significant role in decarbonizing also, heavy industries, switching fuel, high grade fuel to hydrogen, large vehicles, rails and trucks and ships and aeroplanes and others, could also move towards hydrogen, where battery technology is not quite there yet. So, well, I talked briefly about hydrogen again, very high level, but in order to transition into hydrogen, there are so many challenges, technical and economic, and these hurdles are every step from production of hydrogen, storage, distribution, and use, and of course safety concern as well. Even though they are in the same range as natural gas, and we are using natural gas for a couple of 100 years now in UK, it is somehow perceived as a more dangerous gas. So there's a lot of things need to fall in place for this industry to pick up. From an instrumentation point, also, this is a very tricky gas. So simply adapting or tweaking some existing instruments that are built for other gases and stuff might not be optimum, and there's a need for developing bespoke instrument. So with that kind of background, I'll give a very, very high level overview of the products that we are working. So we are basically building a measurement platform. So we kind of bucket our product development into sort of three compartments. One is hardware. So we've literally the last 8 months taken a step back and see, what do we really need to build as a hardware if you're building for unconventional gases like hydrogen, and also adjacent industries like carbon capture and others, where you'll have a requirement to suddenly start metering, the industries, heavy industries capturing their carbon, and that needs to be metered in order for carbon tax, etc. So what we are heavily focusing on is building advanced new hardware, putting our 35 plus years experience in sensor design to really build bespoke hardware for measuring unconventional gases and as such in different settings, and then the algorithms or the software needed to get the best out of this hardware. They are closely connected to the hardware. Those are the two areas we are heavily investing at an IP level and having proof of concept prototypes developed, etc. And we are really leveraging all the fantastic technology advancements that are happening in adjacent areas such as IoT and communications by adapting many electronics and analytics platform to position our products. One of the things what we wanted to sort of tell or mention in this talk is that when we develop this platform, it's important to capture a lot of use cases. Our technology that we are building at the moment, our intention is to make the hardware really economical and easy to manufacture. So we are applying a lot of novel ways to manufacture the sensors, so that's highly scalable. So the actually measurement that needs to be implemented, whether it's in a factory or in a distribution line, etc., can be very economical. So you can really move away from a single point measurement to a multi-point measurement where you can get a much better understanding of what your processes are. And with a small team of around 5 people working, we are focusing heavily on 1 or 2 use cases, starting with hydrogen refueling, for example, is one use case we are working on. We are leading an Innovate UK award funded to build a new prototype concept. And similarly, we are also looking at domestic meters and industrial meters. What would be nice is if there are some tricky measurement processes and challenges that the foundation industries have, we'd love to hear about them. After this, you can contact us through our website or LinkedIn page or drop us an email, and love to look at possibly building our platform to be applied for your use case. With that, I'll stop and happy to take any questions.
Thank you very much. Yeah. Just one question for Nishal, and then we'll move to the break, which is scheduled next. So, does anybody have just the one question to send in? If not, hydrogen, absolutely. It's very, very clear why you'd want to control and understand the flow of hydrogen. It's kind of important if you're going to apply that technology. Well, we will apply that technology, of course. Where else in the foundation industries might you anticipate that you could use your technology?
We are hoping, there might be areas where we'll be replacing the existing fuel by replacing to hydrogen for high grade heat and areas like that, because carbon emission and if there is a green source of hydrogen available, that's one way this can use.
What about in the industry, Nishal, in the flow of liquids in the chemical industry? Is this already used?
It is already used in some industries, but not I guess as widely as others, I suppose. The other general uses, even powering instruments and stuff. So one of the things we are looking at is how do we use our instruments and measurement platforms to be even powered by hydrogen, for example. So in one of the earlier talks, they were mentioning about energy harvesting, etc. So even larger power hungry systems, if you can make them autonomous or derive power from hydrogen, there's an opportunity to build some capability into it. And that's the kind of area we are looking at the moment.
Okay.
And in general, not only hydrogen, even looking at carbon capture. So if some of these heavy industries are looking to slap CCUS on top of what they're doing currently, there's a necessity to, again, monitor what you're capturing, what are you shifting out of your factories, etc., for, fiscal or some sort of carbon budgeting regulatory requirement. And again, it all requires a bespoke measurement platform.
Thank you very much. There is one question here from Trevor Bean. Don't do this verbally, but if you could type a response to Trevor, which is, could this be used in complex foodstuffs inside pipes? So if you could just type a response during the break, Michelle, that'd be great. Thank you.
Sure.
We just need to move on to the break to give people some time to do what they want. And we'll come back and restart. I think we're running a little tiny bit late. So if we say 20 past, Yufeng, is that okay?
Yes, yes.
Okay, so we'll start at 20 past because we're running a tiny bit late. I didn't want to not have questions for you, Michelle. You needed to have some questions. Okay, so now a break now. Welcome back, everybody. So we're now going to move on to our next presentation, which is going to be from Yufeng Lai, who is from the University of Sheffield, my own university. He's a member of the Sensor System Group, and he's going to be speaking about the thermal and dimensional metrology in liquid steel making. Are you going to share the slide yourself, Yufeng?
Hello, hi.
Hello. We can't see your slides, Yufeng, so we need to see your slides. Yep, they're back there. Good. You're good to go.
Okay, thank you very much for the invitation to do the presentation today. Good afternoon. My name is Yufeng Lai. I'm a member of the Sensor System Group in the University of Sheffield. What our group doing is to develop the thermal metrology both in the software and the hardware wise, and imply them into the industry and the research use. We designed the optical system, temperature measurements, emissivity measurements, and the hyperspectral imaging, and so forth. My talk today is about the thermal and the dimensional metrology in liquid steel making. The work was carried out with Tata Steel in Port Talbot in South Wales. In this talk, I will introduce the background of these projects and the long-term objectives in the first section. And after that, I will introduce the current work we have doing and what we have achieved, which are implied in the center plant, the Blastophonics plant, and the steel making plant. As we know, the steel making has many different processes and components. The reasonable optimization and process control could significantly cut the cost, as well as improve the quality of the products. It's our long-term aim to achieve the full coverage of optical sensors that can build contemporaneous data for the dimensional, thermal, and the chemical makeup of the feed, store, and output products for each step in this process. This data should form a necessary and sufficient suite of information upon which to fully optimize the steelmaking process of any particular alloy. We now have been worked with Tata Steel in the past 2 years and help many experts by taking our advantages of these technicals. And today I would like to present the project we have current work on, which is implied in the center plant, the Blastophonics plants, and the steel making plant. The first project, we design and install 2 cameras in the center plant for produce contemporaneous data. The first camera is a color camera, which was customized for monitoring the dimensional distribution and the color of the center. Another thermal imaging camera is developed for tracking the center and monitor the burning front that produce porous material in the center size. Our live video, along with analysis data, are shown in a web page by helping with this technical, the industry could monitor the process in the synthesize on time and optimize their procedures. Here is the design of the synthesize camera. It contains a color camera itself and the designed lens, a powerful PC, and the customer the air purge for removing the dust. And this instrument has been installed in the top of the conveyor and supplies a live video while this conveyor works. And I would like to show the image processing we designed for mirroring the synthesize. First, we pre-process the raw imaging by choosing the conveyor edge and normalize the illumination. And then we mark the foreground and the background by a series image processing. And then we use watershed algorithm to detect the rock. Here, please have a look of our output video in the web page for the industry use, which includes a live video, the detection mask, and the output of the watershed algorithm. In the right of the page, we also calculate the synthesized distributions. Our synthesized camera has been worked fine on sites for at least 1 year and supply many useful information for their procedures. This is our second camera in the center plant. The designed thermal camera we used here is for mirroring the temperature distribution and the burning front in the center conveyor by its thermal intensity of the camera. Besides, we designed an air system which could supply the positive pressure in the front of the window and keep the room clean all the time for the observation. This instrument is has been installed in the front of the conveyor and to monitor this procedure 24 hours. This is our image processing program. Firstly, we correct the effect of the dust. As we know, this is really dusty conditions. So each imaging, we will correct the intensity by the dust. And then we track the top edge of each pellet, counting the conveyor speeds. This is used to estimate the pellet speed and detect if the pellet has already dropped and mark the timing of it. And then we're tracking the bottom edge. Here is example video shows our output of the thermal camera in the web page. This page includes the raw imaging for tracking the burning location, which show in different color of light. It's left top of this page. And then the thermal imaging shows the temperature distribution of this process. In the right of the page, we calculate the statistic data, for example, the intensity and the location of these burning fronts. As we see from our algorithm and this thermal camera, we can precisely tracking the burning front, where is it, and the pellets length. The second project we are working on is for the Blastophonics plants. Inside the Blastophonics, we monitor the conversion to liquid iron by means of the novel thermal image camera. We aim to use our technical to monitor the reactions inside the Blastophonics by the temperature and other analysis, and help the industry to adjust the oxidizer and fuel. For long-term we plan to install 30 thermal cameras around the 2 locations to monitor the process in different angles of view. This is radiance calibration based on Planck's law we made in the lab. We have done several calibration, use different explorer time in order to fit the various flame temperature situation. And here is the video shows outputs of this project. And because this camera was installed in the tool location and look inside the furnace, we can clearly see the injection lens and the coke out from it. We also highlight the highest temperature zoo, which indicates raceway, and in the raw video here. On the right video, the flame it shows the flame temperature distribution based on our calibration process. The last project I would like to introduce is at the steel making plants. We install a thermal camera to monitor the liquid iron and also the slag extraction process. Also, this thermal imaging was used for the ladle access, so it would help the industry to evaluate its service status and the timing for reline. This is quite important because the right timing of the reline can significantly save the unnecessary expense. Here is our instrument that's already installed in the desulfurization site. The picture in the right shows slag extraction process. Considering the surrounding temperature is quite high and there is strong radiation emitted from the hot iron, we also designed the heat protection part, which includes the heat shield, instrument blankets, and the temperature loggers. We have calibrated the thermal camera and make it available to mirror the suitable temperature range. And this is the output video shows slag extraction process, which is captured by our thermal camera. The live thermal video could help the operators better distinguish the slag out from the liquid iron. The unnecessary waste of the iron during this process could be reduced. We also expect to do further image processing on it in order to better classify the solid slag from the liquid iron. The ladle that's used to transfer the liquid iron need to be cooled down and assessed before use every time. Our thermal camera captures the images while the ladle is under cooling, and we select several regions of interest to represent the different material for the emissivity estimation. After the calibration, we also analyze the mirrored temperature residuals, which is caused by the different emissivity estimation. This is cooling rate of different material from our temperature results. It shows the region of the slag and the refractory has distinguished cooling rates. So our emissivity correction could supply a more accurate temperature results. Before this, besides this, we analyze and see the slag dropping process phenomenon during this cooling process, which is shown in the red circles. We have found there was a temperature change before and after the slag drop. From our statistic results, the industry could better control their process. At the end, I would like to show an example video we captured while the ladle is under cooling. Thanks. Thank you very much for your time, and I'm happy to discuss if you have any questions.
Thank you, Yufeng. That was really interesting. Yeah, I am familiar with some of John's work, and now I'm familiar with how your work as well. So that's good. So, are there any questions for Yufeng? If you can post them in the chat, that'd be great. In the meantime, you've been mainly focusing on the steel industry. Are there any other industries which have you feel that some of your thermal imaging cameras and your digitization is going to be important in the future?
Yeah, because especially for the steel making, this process is have a very high requirement of the temperature monitor. So by using our technicals, we can help to control these, monitor these, and control these, and help the industry to adjust their strategies to, like just like the Blastophonics. Inside that is for the industry, they don't know what happened inside, but from our cameras we can see if the oxidizer or the coke is have a balance, so they can adjust their strategy out from this.
Are there any other sectors that you could interact with other than the steel industry? Have you thought about interacting with the glass industry?
Yeah, I think we have planned that we currently do these 3 projects, but we have planned to do more, like use our technicals to monitor the like the steel making process that is really needs the temperature results. Also, we can analysis components of these chemical components of these by our hyper spectrum imaging.
Okay, so thank you. If there's any more questions for Yufeng in the chat, okay, here we have one that's come through now. This is from Steve PW. What is the accuracy of thermal imaging plus or minus % degrees C? So,
this depends on different wavelengths and the temperature range, but overall we make our instrument is under 2% residuals, but in small dynamic range cameras we can make it better, like 0.5% residuals.
okay, so about 0.5 depending on wavelength. Okay. Okay. Thank you, Yufeng. That was really interesting. And it's nice to see stuff coming out of Sheffield, of course, from my perspective. So we're going to move on to our final speakers of the day. We have a joint presentation, which is, I understand it's joint anyway. It's going to be from Professor Zhishang and Dr. Alison Norden. And this is going to be from Dr. Alison Norden, who co-presented by Dr. Alison Norden, who's a reader in applied chemistry at the University of Strathclyde. She's the technical director of CPACT. I'm afraid you're going to have to ask Alison what CPACT stands for. And her research interests include pressure analytic technology, spectroscopic technology, and applications in that area. Dr. Zhishang is a reader at the School of Engineering, Newcastle University, and he has interests in process control, data-driven process modeling, and process monitoring, amongst many other things. Are you okay to present yourself, or is Debbie going to forward these things for you?
Yes, okay, yeah, I'm sorry.
Okay. You okay, Zhishang? Alison, you guys go ahead and let's listen to your talk. Thank you.
Okay. So firstly, thank you very much, Ian, for the introduction. So as Ian's already said, Jay and I are going to deliver this presentation jointly. So both of us are from the Centre for Process Analytics and Control Technology, and we're going to try and show you how multivariate statistical process monitoring and slow feature analysis can lead to resource and energy efficiencies in the foundation industries. Just very quickly, having said what CPACT is. So CPACT is an academia industry consortium. It was founded in 1997. We currently comprise 33 industrial members and 15 academic, university and research institutes. And I think it's fair to say that we're the leading network for companies seeking advice, training and research in process monitoring and control. Next slide, please, Jay. Thank you. So just a very brief outline of the presentation. First of all, give a brief introduction to the outline the energy and the emission requirements in the foundation industries and hence set the scene. Then I'll talk a little bit about multivariate statistical process monitoring and its basis in terms of principal component analysis. Then I'll talk a little bit about some of the tools that have been developed in CPACT that are based around multivariate statistical process monitoring. Then mention one particular tool called slow feature analysis, And then we'll also talk about how multivariate statistical process monitoring has been applied to a coke oven monitoring problem specifically, and finally some conclusions. So just so the foundation industries, they produce 28 million tons of material per year in the UK. That contributes £52 billion annually to the UK economy. So they're clearly a huge contributor to the UK economy. However, they're one of the biggest UK industrial polluters. So they're responsible for 10% of the total of the UK emissions in terms of carbon dioxide. Just as an example, the steel industry, a coke oven in the steel industry, it's a major contributor to NOx, sulfur dioxide, carbon monoxide, carbon dioxide, and particulate emissions. The foundation industries as well, they also consume a lot of raw materials and energy. Clearly, it's very topical at the moment. Sorry, just back one, please, Jay. Sorry, Jay. Obviously, very topical at the moment with the upcoming COP26 in Glasgow. So achieving energy efficiency and emission reduction is of vital importance in the mission, not only to achieving net zero in the UK, but when you consider the consumption of raw material and also energy, that's really important for the foundation industry in terms of the competitiveness of this industry specifically within the UK. Thanks, Jay. So process monitoring and control, this plays a really important role in how we can make the foundation industries have higher energy efficiency and also reduce their emissions. So if you basically can devise methodologies that enable you to detect faults earlier in any type of actually industrial process, that means you can have a significant reduction in energy efficiency and also the amount of emissions. One of the challenges, though, with many industrial processes is a lot of the variables are highly correlated. So it's actually really difficult to monitor, just say what you can't monitor one particular variable and understand then what's going on. So this actually makes process monitoring and fault detection and actually diagnosis of a particular fault quite a challenging and difficult task. And this is where multivariate statistical methods and machine learning methods, which are obviously very topical at the moment, these come into play as they're very effective in dealing with large amounts of process and actually other types of data such as spectroscopic and many of the instrumentation measurements that some of the previous speakers have talked about. Thanks, Stu. So multivariate statistical process monitoring, this is can actually very effectively be used to monitor a wide range of processes. It can be used to give you early warning of process malfunctions. It can ensure that you have consistent production of a particular product, so you have less waste, you can produce more of what you want more often. You can have improved usage of plant assets as well. So traditionally, multivariate statistical process monitoring, it's been based on principal component analysis, and then it's been extended to nonlinear versions. Traditionally as well, it was always used more commonly used with stationary process. Again, it's been extended to non-stationary processes. But in its simplest form, what we're basically doing is using the correlations between these different variables to produce these new variables, so-called principal components. And this reduces the dimensionality of our problem. So we can go from hundreds to sometimes thousands of variables down to just a few principal components. And what we do is we build a principal component analysis using the data that's collected of a process functioning under normal operating conditions. And then what you do is you project new data into this model. So the monitoring is done within principal component space. And we commonly use two statistics in order to detect faults. And these are the squared prediction error, or the Q statistic, and also Hotellin's T-squared statistic. So we can use these to identify a fault, and then we can diagnose what the cause of that fault actually is. Next slide, please, Jay. Thank you. So CPACT has pioneered a lot of this work in multivariate statistical process monitoring. This was mainly through the work of Professor Julian Morris and his team at Newcastle, which includes people like Jay. Much of this work it was started in the 1990s, and CPACT has produced a number of software tools that allows application of these multivariate statistical process monitoring methods across a range of industries. So, for example, one of our software tools that's widely used is called Prescreen, and this is because it was estimated something like about 75% of time is spent actually screening industrial data and looking to detect missing data and pre-treating this before you actually go on to build your models. Then colleagues at Newcastle have pioneered software packages such as Multidat. This is a principal component analysis based monitoring method for looking at continuous processes. And then there's BatchDat, which is a method for looking at batch process monitoring, and it deals with unfolding of data and also handling of uneven batch lengths. Thanks, Jay. So actually, obviously the focus here is very much on the foundation industries, but these methodologies that Jay and his colleagues at Newcastle and Julian in particular have pioneered, they've applied them across a wide range of industries. So this slide here is just really to give you an idea of the range of industries that some of these methods have been applied and some of their business benefits. So for example, the top one, savings in catalyst usage in a commercialized scale fluidized bed, that saved BASF something like £1 million per year. Looking at Unilever, being able to detect through using these methodologies that allowed them to detect a faulty reactor dosing, that's saving £250,000 a year. Being able to understand where unexplained variability in fermentation processes was coming from, that saved something like £4.5 million per year. There's also been work done with high performance, high speed polymer sheet production that was done at DuPont and what was UCB films. That resulted in significant reductions in off-spec material. And then finally, the example with Chorus, that's led to significant operational cost savings. So hopefully that gives you a flavor of the range of industries. Now I'd like to invite Jay to talk specifically about how these methodologies have been used for coke oven monitoring.
Okay, thank you, Alison. So now I will talk about using this MSPC for coke oven monitoring. So coke is an important material in iron steel industry. So we use coke in blast furnace for iron making. So coke is produced from coal in this coke oven. So basically we charge coal into this coke oven, and so the coal is carbonized in the oven for about around 18 hours, and then they pushed out from the oven and quenched. So the heated oven will transfer heat from the burning chamber to the cold chamber. So basically, we transfer the heat from the burning chamber to the cold chamber. And also we have typically we have multiple ovens, so they are arranged in this battery. So basically, we got one oven next to another oven. So that's for the energy efficiency. And the off gas, which is the raw coke oven gas, is sent to a byproduct plant, which cleaned, and then the cleaned coke oven gas is used as a fuel in this coke oven. So this picture shows this coke oven from Tata Steel at Scunthorpe. So here we have 3 batteries, and we have 25 ovens in each battery. So altogether there are 75 ovens operating. And so the cooking time is about 18 hours. So that means every day there are 98 ovens being pushed. So the capacity, like production capacity, is around 690 kiloton coke per year. So, sorry. Okay. Yeah. Okay. I think probably got one. Yeah. Okay. So, so the one problem with coke oven is the through wall leakage. So basically, the oven wall can have sometimes can have a crack. So you got leakage between the burning chamber and the cold chamber. So basically, the some of the material from the cold chamber can transfer into this burning chamber. So So this will cause will increase in the emission and also the incomplete combustion in the burning chamber. So therefore, it can increase the energy consumption. So therefore, it's important to detect this through leakage as quick as possible. So traditional method for inspecting oven wall leakage are those methods. So the first one is stack smoke emission during the oven charging. So basically, stack refers to the larger chimney in this coke oven plant. So sometimes if you have a larger crack in the coke oven wall, and if that oven is not very far from the stack from the chimney, then sometimes you may notice that when you charge the coal into the oven, then soon after that you notice a black smoke coming out from the chimney. Okay, but this method is not always possible. It's only like when this when the crack is quite large, so you got quite high emission, and also when this oven is not far from the stack from the chimney. So if you got like a small crack, and also if the oven is quite far from the chimney, then you may not notice this black smoke from the stack. So therefore, this method is not it's only like possible for high emission for larger crack. And the second method is inspection of oven chamber by the push driver. So when the push driver push out the coke, so he can quickly inspect the wall. But because the coke oven is operating at a very high temperature, so it's not easy to inspect like by the operator. So it's quite subjective, and also only a small crack will be missed. The third method is inspection using camera and parameters. But this one you need these specialized tools, and also need experienced personnel for this operation. And also, once again, because this oven is operating at very high temperature, so actually you can only like use this camera and for like very short period. You cannot like put this camera in this oven for long period. And the fourth method is by analyze the waste gas from the individual wall. And again, this one needs specialized tools and personnel. So here we use a data-driven approach. We use a multivariate statistical process monitoring and machine learning techniques. We analyze process data and try to discover those leakage earlier. Right. So we have many months of process operational data from Tata Steel. So those are continuous data and discrete data during the each oven pushing out. So it's a big data problem. We got quite a lot of data. We got mixed type of data. And as Alice mentioned, so data pre-screening is very important. So because this oven is operated at a very harsh environment with high temperature, so actually some sensor will fail during the operation. So we need to detect any like missing data and the outliers in the data. So finally, after data pre-screening, so we selected 20 process variables used for this MSPI, and also we downsample the data. So in the plant, so basically they log the data every 5 seconds. So we downsample to 1 minute. Okay, and the coke oven wall leakage is typically indicated by high stack CO and high stack dust emission. So basically here we use a stack emission data to divide the data into a normal data and abnormal data. And we build a PCA model on this normal data. So basically we use a PCA model to reduce dimension of the variable. So here we reduce dimension from 21 to 4 principal component. Okay, so this picture shows this. We use this CPAC software multi-data to analyze the data from the coke oven. So here in this in the middle, you will see this. You got this squared prediction error (SPE), and you got this T-square monitoring statistics. So the blue line represent the normal operation. You can see they are below the control limits. And then here you will notice that the monitoring statistics exceed control limits. So that indicates something wrong. So we can detect this problem using this large SPE and the large t-square values. And so this plot on the plot on the left represent in the principal component 1, principal component 3 in this space. So the blue point in the middle represent normal operation, and you got this control limits given by this ellipsoid. And any point outside this control limits represent you got abnormal operation. Okay, so here you can see we got quite a few samples with high Pca3 value, and then we can using this software package we can look at the contribution, different variable contribution to Pca3. So that's a contribution to Pca3. So we notice variable 21 has a very large contribution to this Pca3. So this contribution plot indicate stack obscuration has a high contribution. So basically this stack obscuration measure this so how clear you can see through the gas and the flue gas. So that indicate probably there's a high emission in the date, and it's likely you got oven ware leakage. But as I said earlier, we got 75 ovens. So which oven has this leakage? So now we need to look at some other like date. Okay, so here we look at the date around this time. So basically this circle represent in the previous slides. So analyze this, we show this part of date, and also we look at this stack dust emission date, and we notice that each time when oven number 6 is being loaded, there is a sharp shoot in this dust emission value. So by examining the time of detection using this principal component model, and the time of the oven loading, and also the contribution plot and other process information, so we can conclude this oven 6 has this leakage problem. Okay, so therefore the process engineers they can try to repair this leak. Okay, so apart from this principal component analysis, so we can also use some other advanced machine learning techniques. So one of these techniques is called the slow feature analysis. So this one is a slow feature analysis is introduced back in 2002. So it's quite a relatively new machine learning technique. And one of my collaborating research group in Tsinghua University in China, so they apply this technique for process monitoring. And also here in Newcastle, so my PhD student and we also propose integrating this slow feature analysis with neural network for soft sensor development. So this slide shows this the idea of this slow feature. So here we have 4 variables. So you can see the driving force are sine t and cosine 5t. So you got those driving force, and then the rest are noise. So by using slow feature analysis, we can discover slow feature 1 is sine t, and slow feature 2 is cosine 5t, and then the rest are noise. So we apply this to this the monitoring of this coke oven. So we compare with the Pca based monitoring. So this one show a Pca based monitoring. So here the blue point represent modeling date. So we use those blue point build a model, and then the red one are monitoring date, and the initial red one are the normal during the normal operation. You can see they are below the control limits, and then when there is a fault, you can see the t-square SPE they are exceeding their control limits. But you can see there are some points they are quite close to the limits, and some point below the control limits. By using this slow feature analysis, you can see we have a quite clear detection. So you can see for those from this monitoring statistic, you can see all samples they are above this control limits. So that means we can detect the problem with a much higher confidence. So finally, to conclude, so here from this example, we can see that this multivariate statistical process monitoring can detect and diagnose operation problems earlier than you observing on individual variables. And also with slow feature analysis, we can detect the problem more clearly and earlier. And the technique can also be applied to many other industries, foundation industry sectors. And also we need further research on integration with other machine learning and big data analytic techniques. Okay, thank you for your attention.
Thank you very much, Jay. Thank you, and Alison, of course. So we have just time for a couple of questions directly for Jay and Alison, and then we'll move on to the broader Q&A session, which applies to everybody. So if we can take a couple of questions specific for Jay and Alison. I do know it takes a time for people to type, so whilst doing that, what would be your next target industry? You're working with the steel industry and this coking factory, but what is the kind of priority list of things you'd like to do?
Right, actually, I think as Alison mentioned, so in the past we applied this to a lot of chemical industry, and so we can also apply to like any other foundation industry, like so maybe like a glass and cement. So maybe I think any other type of industry can be benefited from this approach. So it's right. I mean, the next target depends like if so which industrial sector has this urgent need and need like a collaboration with the CPAC, then we can try those.
I think the foundation industries all need this kind of approach to try and improve monitoring processes. It's really important. So I would heartily encourage all the members who are here of the network and the people who work in the foundation industries, if they're interested in this work, then please contact Jay and Alison. It's important stuff. Okay. There's no specific questions coming in for Jay and Alison at this present moment in time. So let's move on to the broader Q&A session. Now, we've had quite a lot of chats throughout, so don't feel obliged that you have to ask questions now. But if you have any burning questions that have come up in your minds as you have been listening to these talks that you didn't get a chance to ask the whole set of speakers today, please do so now and type in some your questions into the chat function. I guess while people are considering that, I guess this is a question for everybody. There's lots of different techniques that we've seen today. We've had ultrasonics, we've had your statistical variation, or forgive me if I misrepresent you, Jay and Alison, but your statistical methods. We've had imaging cameras, we've had photonics. Is there a need to have all of these things being applied to some of the foundation industries, or are they mutually exclusive? Do we need one is best for some, one is best for other industries? How could we combine these things? Because there was a message that came through from Sarah Connolly about the demonstrator program that is going to be run by the Innovate UK. That's a £5 million grant that you're going to be able to for big ticket items that are going to be for the future of the foundation industries. And I guess some of these things would need to be combined and put onto these demonstrators in some form or another. So is it worth the digitization and these monitoring and sensors community getting together and deciding what is best for any given set of particular sectors? Is that something that happens within your area of research, or perhaps that's something that needs to happen? Could a response from the wider speakers today would be fantastic.
I can make a comment, Ian. So it's Alison Norden. So just certainly within CPAC, we found that the success, our most successful projects have been when we've got people who are doing research in measurement techniques. So we make the right measurements of things that we need. We then combine that with appropriate data analysis techniques so that we can extract the maximum from these measurements. And often what we find is that no one measurement can measure everything, and particularly a lot of the processes that we work with across the range of industries, they might be multi-phase. So there could be different chemical things that we want to measure in different phases. There'll be different process variables that we want to measure. So therefore, we need advances in different measurements so that we can measure the things that we need. We then need advances in data analysis so that we can then extract the maximum we can from that. And then we can use that information for process monitoring, process control, development of processes. And as I say, I think these needs are across a wide range of industries.
That's the impression I've had today, Alison, that you've got a lot of solutions to some things, and in combination with some kind of overarching statistical analysis of what's going on, you really have something very powerful that could become part of a demonstrator project for one of the foundation, or multiple sectors in the foundation industries, preferably for those projects.
Totally.
Sorry, who's that? Sorry, who's that?
Sorry, it's Nishal here.
Nishal, you.
I just want to echo Alison's comment. Totally agree with the suggestion that at the moment the industry is kind of disjointed. Everybody's one sensor technology working on its own, but already we can see a lot of change happening where multimodality is getting looked at quite heavily. Alison mentioned gas composition along with flow measurement of fluid properties and stuff like that in one single spool piece or measurement instrument would be really good. And some of the underlying capabilities that are happening, like pushing, for example, advanced analytics to the edge and processing the data and giving out a reliable output can happen nowadays. It was not possible 10-15 years back. And I think that'll be a huge enabler to combine, for example, photonics with ultrasound and others. And this is something that should be highly encouraged, for sure.
Sure, there's a lot of conversations happening at the moment about these demonstrator projects amongst the foundation industries. So I think if you want to chat with us, we can certainly act, actually it's our jobs, to be fair, to act as a role of a kind of a liaison broker or a relationship broker to try and connect you to the right people to maybe get involved in these and maybe have combinations of these sensing and control systems and these statistical analysis systems that really could make a difference in the, these demonstrators are effectively trying to create, foundation industry 4.0, which is what they're trying to do. So we have a sustainable industry for the future. We can't do without steel, we can't do without cement and concrete and so on. This is the building blocks of our society. So the more sustainable we can make it, the better, and these demonstrators are all about that. So we're very happy if the speakers of today or anybody listening on this particular workshop wants to come and chat to us, and then we can maybe contact on your behalf or act as an introductory service on your behalf to certain companies and academics if it's an industrialist coming in the other direction. So I think that's really important. Would any other speakers like to comment on that approach?
Can I?
Hi, Chris, you go ahead. Sorry.
So I'm manager the Digital Technologies group at the Materials Processing Institute, where we're effectively building a industry 4 demonstrator for the steel industry. So we were Tata Steel's Process Research Centre. So I was very interested to see the most recent presentation was one that was led by one of our colleagues within the Tata Steel Research Centre. And now we have funding for creating we have our own pilot-sized steel plant. So it has all the legacy foundation industry issues of connectivity, multiple platforms and sensors, technology, etc. But we are actively engaged in trying to build a steel plant demonstrator there for Industry 4. And if anybody would like, the idea being that things can become and tried out on a pilot scale. So it's 7 tons rather than 150, 105 tons on the full size steel plants, but has all the same harsh environment issues, etc.
Okay, thank you, Chris. So actually, CPAC, I think CPAC in the past has worked with Tata Steel and previous called Coros and British Steel.
Yes.
So we had quite a few KTP project, and also this actually the one I presented is a European Union funded project. So yeah, so actually I think we worked with Swindon Technology Center near Sheffield.
Yes.
Yeah, that's right.
Swindon was our sister site. We were Teesside and they were.
Oh yeah, Teesside. Yeah, also we have.
Yes, so yes, we worked together in the past, organisation wise. So yes.
Yeah.
But like I say, we have Innovate UK funding through a program called PRISM, and one of the streams of that is applying digitization to the steel and metal sector. So, you know, I would invite people to look at our website and to have a look at there, because there's you know, work we can do on that program.
Chris, a bit of a leading question. We have a call coming up in the new year. This is going to be after the demonstrator EOIs have gone in, so this is separate from that. But so we have a call in feasibility projects coming up, in which will include some digitization, sensors, control systems, and like that. Are you interested in acting as a partner on some of those? If we can find some academics who, well, you have seen some academics today who have interesting ideas and concepts.
Yes, you know, we are. I'm aware that there's this TFI demonstrator call. I think tomorrow there's a manufacturing made smarter, sustainable smart factory call.
There's a couple of knocking around, Chris, for sure.
So there are several calls in there, and as well there is the possibility that this PRISM funding is being granted to the Institute for 5 years of academics or the SMEs, etc., leveraging some of that PRISM funding to work with us. So there's multiple possibilities coming up. It's a good time to be looking in these areas.
Yeah, there's a short lead time for some, but I think our TFIM Plus is going to be probably around Feb. We'll be advertising that soon enough. So if people can't move quickly, there's another one coming up that perhaps could be a good vehicle for this type of collaboration. From what I've heard today, there's some fantastic stuff out there, and I think if we can get multiple different control systems in the right place, on the right systems with the right multivariate statistic process monitoring, we can do some great things.
Can I briefly comment, Ian, just going back to what you were saying? You know, one of the things from our point of view is, as you probably guessed from my presentation, we are not experts in foundation industries, but we do have a toolkit of things, capabilities and techniques. So we're probably not able to sort of lead a discussion on what is the best technique, and you know, we're not going to force ourselves upon, you know, a solution. But what would be useful from our point of view, and maybe others, is a sort of, whether it's a list or a sort of, you know, a sort of challenge pool, and what the things that are difficult to do right now might be handy as well, for those who might be adjacent to the sector but not embedded in it, but might have some things to offer.
And one interesting possibility could be that we get an academic to do a feasibility assessment of the varying technologies for certain given applications, and to see what comes out. You know, we've done position papers like that before on different things. And from my group, I am not expert in digitization or sensors and controls, so I couldn't possibly do that myself. But we have done position papers where we look at the various benefits and advantages of certain systems and certain technologies, and that sounds as if it's something that would be incredibly beneficial. So if there is an academic out there who's interested in getting some funding to look at these digitization technologies, to see what is an idealized version that could help, that would be something that would be interesting in seeing as a proposal. We cannot guarantee anything. We seek to get proposals in, but we only fund those that pass the quality criteria for our reviewers. So that's my disclaimer. I'm sorry about that one. I have to say those things. So, are there any further questions?
Yeah, Ian, can I? Sorry, it's Mark. I just wanted to make a comment. The Transfire Hub, which is the parallel research and innovation hub to the TFI Network Plus, is actively talking to PRISM at the moment about how we can work together. So that is something that John Bolton, our chair of our stakeholder steering group, made sure happened. So we are actively talking to PRISM at the moment, just to make sure people do know that this is happening. And, there are ways through, of course.
John being chairman of the Institute board,
exactly,
council does help.
Exactly. Well, he chairs our stakeholder steering group as well, so that may be something you weren't aware of. But
thanks, Mark, for that comment. That's really good. It's great that it's going on already, but if we can get more things going, all the better.
Absolutely.
Okay, where are we? I've not got my chats up here. Okay, right. Anything else to ask for these speakers today? I learnt a lot, that's for sure. It is not my subject area, but it is intuitively incredibly important from my perspective that we optimize the processes that we have. They are going to modify a little bit these processes as we improve energy efficiency and things like that, but we're still going to be making steel at whatever temperature steel is made at and firing ceramics at high temperatures. The glass only melts at certain temperatures. You know, we're not going to change those things. So we need to improve the processes that are involved and make them more efficient. And these technologies are clearly pivotal in that.
One comment from me.
Yes, please, you go ahead. Just interrupt me if I go on too much.
We'll be very pleased to discuss with colleagues and industry about specific needs and requirements for designing bespoke systems for self-power sensing, particularly from locations that are hidden, hardly accessible, and require monitoring of different types of data. So.
Okay, we're now drifting past the nominal closing time. So I'm going to draw this to a conclusion. I think we've had some really positive talks and some fantastically positive responses about collaboration. And there's existing stuff with the Hub and Prism. So that's already fantastic. So let's thank our speakers virtually. They've been marvelous today. I think it's been a great set of talks. I'd like to thank the KTN for co-hosting, co-collaborating on this workshop. KTN very much were one of the main organizers, and we did this very much in tandem. So you have before you today the KTN details, as well as our own details for the Network Plus email address, webpage, and our Twitter handle if you want to find out what's going on. You can, Debbie does a marvelous job of sending out various tweets about the activities that we're doing at any moment in time. So it only remains me once again to say thank you very much, and let's digitize. Okay, so bye everybody.